Hello again, here we are as promised, the third part of this first question one of the car questions. So in case you're getting stuck on these, we have done part A and B in the previous video, so this hopefully shouldn't take very long. We've got the last part C. Now it is 6 marks, so it's quite a big old question. I'm going to keep my diagram handy here. This was what we had in terms of what's going on while the whole system is pootling with its 0.7 acceleration. Part C, we're focusing on that again. It says when the car and trailer are moving at 12 meters a second, so that's its velocity, the tow rope brakes. Assuming that the driving force on the car and the resistances are unchanged, because in reality that could change things. Let's find C, the distance moved in the first 4 seconds after the tow rope brakes. So a lot has changed. Our system is not doing what it was doing. The car is no longer attached to the trailer, and it's the car we're interested in. But notice we're starting to get velocities and time, and they're asking for distance. So this should be ringing bells that we're no longer just dealing with force, mass and acceleration. We've got a sort of speed and a time in there, and we want to find a distance. So that's going to be a suvat thing. So I'm going to redraw my car, which is now whizzing down, but they haven't actually noticed that the trailer's popped off, and so it's still driving at the same speed. I suppose for 4 seconds you might not notice. So there's no tow rope anymore on this end. All we have is the original resistance that the car has, which is 630 newtons. So that's still there. So if something changes, good idea to draw a new diagram. We've now got this scenario of this car pootling along. Now, what that will have changed, of course, it's still going this way, but its acceleration may have changed because the forces have changed. So let's do a little suvat analysis and see what we know and what we don't know and how much we need to work out. So suvat, always the way to write down, see what you've got. Now in the question, do we know the distance moved? Well, actually C is find the distance. Distance moved in 4 seconds. Okay, so no, we don't know the distance, but we do want to find it, so I'm going to leave that in. U, the initial velocity, so are we given that? Well, yes we are. If we have a quick squint back in here, when the car and trailer are moving at 12 meters per second, the tow rope brakes. I'm assuming the trailer itself is going to just be decelerating because it hasn't got its own engine. So you can always try this out, get some trucks out, get something on wheels, start dragging things about, share a video or a picture, if you like, of you playing with toy trains or toy cars. V, we don't know that actually. We're not coming to rest, and we're still driving down the road. So V is the one that we don't know, and actually we don't care that much about. Acceleration, don't know. I have a feeling we could work that out if we needed it. And time, well, we're given that in the question that we have 4 seconds. So easier than velocity to work out. I think I can work out this acceleration, and then we will have the 4 quantities so we can do a remember, we only want one to be absent completely. So can I work out the acceleration of this system? It's now come to a really simple system. So I know what all the forces are. I can use this. The mass of my car is still just its mass, not its mass plus the trailer. It's on its own. So F equals ma. The forward is 2,380 minus the resistive force 630. That's the net force. And on the ma side, we have the mass of 1,400 times the new acceleration. I could call this A2 if I want to be really clear. I don't mind what you call it. Could call it B if you want. I don't mind. Or X. Go for it. As long as you remember its acceleration. So what this gives us is 1,700. And so our acceleration we can work out. Again, I'm not going to do this one in my head. Is 1750 divided by 1,400. 1.25 meters per second. So acceleration still seems like quite a small number, but actually compared to the 0.7 it was before, we've actually shot forwards. So that's the main thing we'll notice when the trailer pings off, is that actually, we're away. Okay, so there's my acceleration in there, and now I can go for my suvat equation. I've got S, I've got U, I've got A, I've got T. Have a look for your suvat equations if you need to look at that. The one we're going to need is S equals UT plus a half AT squared. Remember, these are on your formula sheets. You can always write next to them which letter they're missing. It's got no V in it, that one. Great, so let's substitute into that and we can find S. So S equals UT, 12 times T is 4, plus, feel free to stop and carry on with this any time you like on your own, because you may well be on the home straight here and know what you're doing. Sorry, that's just A, not squared. It's T that's squared, 4 squared. So I've done my substitution, U times T plus half A T squared. Everything's positive here. I didn't look at direction, but I'm basically taking that as positive direction. Okay, so we just worked that out. 48 plus 16, that ends up as 8 times 1.25, that's just 10. So I have S equals 58 meters. That's how far we're going to move in that first 4 seconds. So that's the distance. Okay, so I'm just going to double check my answer. You just let me know if you see any slip-ups in there. Okay, but I'm happy with that. And D, state, let's have a look at the question. It says, state how you have used the modelling assumption that the tow rope is inextensible. So non-stretchy tow rope, inextensible. How have we used it? Well, we used it, I suppose what it was, we said tension for the car and the trailer is the same. So if we had a stretchy rope, what would be happening would be there would be a kind of delay, wouldn't there, that the car could put that amount of tension into a stretchy elastic band. You can also do a little video of that if you want, or a picture of some elastic band trailer tension, and then the tension would get transferred after it had stretched to the trailer, and the trailer would sort of ping back and hit the car. So not a good thing to have an extensible tow bar. So that's how we used it in the question, though. We said that the tension in the car and the trailer tow bar is exactly the same. So it's the same T. Okay. So that's all for that question. Good luck with the others and let me know how you get on.